Good morning, everyone. Can you hear me well? Thank you. So as usual, we will start at 11:10 with a short quiz for 15 minutes. So it will be available for you in 7 minutes. After that, the next step would be we'll start, our tutorial. But I would ask you to provide us some feedback on the course itself. So I would reserve, I don't know, 7, 8, up to 10 minutes of your time to you go online and provide your feedback that we highly appreciate, especially since it's the first time we're teaching this course, online. So your feedback would be highly appreciated. So we will do that. And after that, we'll go back to normal and go over some problems related to the last lecture. Okay. So if there are any questions, please post them in the chat. Okay, hi everyone again. So the test should be available for you now. Please go ahead and start the quiz and see you in 15 minutes. Good luck. Okay, we'll start in a minute. I'm just still waiting for a few more people to finish the quiz. After that's done, we will start. Okay, let's start. As usual, please, if you can turn on your camera, that would be highly appreciated from my end so I can see how we're doing. Okay, so this week I want to start us quickly with evaluation. Most of you should get by now the links for the evaluations. If you cannot get them, here is a link that you can go for and open your evaluations. I would really appreciate if you would go and do it right now, so because that would allow us to get a higher response rate, and we can use your feedback to improve the course in the future and teaching overall at UTSC. So please go and do it right now. And when you're done, you can probably post a message in the chat. I can see how, when most people will be done, we will resume the lecture. Okay, so I want to please spend whatever time you need. I would say probably 10 minutes should be enough. So either go through the link or this link or check your email. Any questions about evaluations, please post them in the chat if you're not sure what to do. Otherwise, I'll see you in 7-8 minutes.
Let me submit. We got what, 130159.
130159. Is it going to be on the 9th one or on the 10th one?
There's a quick question. Are most people done with evaluation, or do you guys need a few more minutes? Can someone please post on chat? Okay, I think we can start now in the interest of time. Others who are still in the process, please gradually finish as I slowly go into their, into the material. So we'll start today's tutorial with a repetition at the end of the last lecture, where we talk about parallelism and pipelining specifically. I think there were several questions on Piazza about it, so I think it would be worth going through that example that I made a little bit more. So remember, when we talk about pipelining, we said there are 5 distinct stages of the simplest possible pipeline, which is exactly fetch, decode, execute, memory read and write, and register write back. And This is essentially led to that figure here, right? So I'll just go over it again and try to clarify it more. And if you were still confused about it in the lecture and it's not clear after this explanation, please ask your questions in the chat. Okay, so there are two ways you can execute instruction. You can do everything serially, right, with no pipelining, right, of any internal parallelism essentially. And then each stage would be executed one by one, and then you start the next stage. What is the advantage of that? This approach minimizes latency, and latency is one of the important metrics. So essentially for that instruction, things will finish faster, and then the next instruction execute. So from the instruction perspective, this is the best approach of doing things. But it's not as good from the throughput perspective because we only do one instructions roughly 950 picoseconds, which just gives us just slightly over 1 billion instructions per second. What is the other approach? The other approach is pipelining. So how the pipelining would work? Pipelining makes the observation that a lot of those stages are independent between each other across instruction. What does it mean? It means I can run fetch for one instruction while doing decode for another one, and I can run fetch when I execute and decode and so on. So just keep using your imagination that we can do in those fetches deeper here. So you can go like more and more fetches. So what latency is, it's about how long you execute from here to here. So it's essentially horizontal. What the throughput is something that we get essentially vertically. What that means? It means that if we had 5 stages in our pipeline, at any moment in time, the maximum, the best case, I can execute 5 different stages, right? So if you look beyond just 3 instructions, you keep going deeper, you might have the situation that something is running fetch, something is running decode, something doing execute, something doing memory write, and something doing write to registers. Because of the alignment issue, so the stages cannot be like half overlap because it creates a nightmare in hardware. Everything has to be aligned. It means that if you look at the latency, every stage now becomes the length of the worst case scenario of the latency. So say fetch and memory has the worst latency of 250. It means that the latency of these instructions now would be essentially 5 of this. So it's going to finish actually not even here, it's going to finish here at 1250. So this is why the latency in this case is 5 by 250. Is there any questions about that? Is this clear to everyone? Any questions about latency? So essentially latency is how quickly I can from point A from point B. And obviously when I start to get this, empty spaces in between stages, it only can get worse. So the latency can get worse. But how about the throughput? Throughput ended up being 250 picoseconds. Why is that the case? Because now, essentially, if you look at the throughput, what you're gonna get is you would be getting horizontally, right? Or sorry, vertically, you're gonna might have 5 stages running on in parallel. So assuming there are no dependencies and no hazards, what you might get is that throughput-wise, 5 different stages executed all in parallel, which makes throughput 5 of essentially 5x 1/5 of the latency, right? So essentially I would be able, if you compute the throughput, right, you would essentially need this latency, right? And would have to divide it by 5 because I can do 5 things in parallel and then multiply it by the frequency. And that's what I get. So essentially, on average, when the pipeline is full, I'm gonna get every instructions 5x faster process than it would otherwise. What I mean process, I mean in terms of throughput, not in terms of latency. Latency for each instruction is slower, but throughput is higher because that's an average throughput per instructions that we're gonna get. This is the average, right? So we would be able to process within this latency of 1 at 1250, I would be able to process not one instruction, but 5. So my throughput would be per instruction would be 250 picoseconds. So the best way to think about it is that my throughput, by sacrificing about 30% of the latency, I get about 5x better throughput than this, or about 4x than that, right? It's essentially like a factory, right? You had multiple people doing just one stage of the pipeline, right? The latency doesn't improve, but the throughput, how many things you can bake in parallel, would improve significantly. Any questions? Well, it's not because it's 1 gigahertz. Essentially, this is a picoseconds, right? So this, this is the latency, right? So if you just take this is 10 power 9, yeah. So essentially, that frequency is kind of already in there, hidden. How quickly you can do fetch or execute, right? But reality is the latency of 950 picoseconds, which is 1 billion instruction per second. This is something they can think of as 1 gigahertz, roughly. But you can see the whole point I'm trying to make, the absolute numbers doesn't matter. The whole principle matters, right? So pipelining is not a miracle, right? It's a known technique. And what it does, it sacrifices in the latency in favor of throughput, right? So for example, if you're in a bakery, what you're trying to get, or I don't know, you go to any of the stores where the pipelining is efficiently done, what they're doing, they're sacrificing the latency of you waiting as an individual customer for the throughput they get overall. So that you might be served a little bit slower by maybe 10, 20%, but they get 4 or 5x increase in throughput, right? Is this idea clear to everyone? Okay, thanks. So because one thing I want to say, why pay attention to the pipeline, this is a principle. If you're going to do systems or architecture of any form in the future, this is one of the big ideas there that's going to be used in many different things. In software and hardware, that's a very important principle that's very frequently used if you optimize throughput, right? It's used in GPUs, it's used in built-in chips all the time. Okay, now in the interest of time, we'll look at just one particular problem to practice the recursion that we learned last time. So this is a code for Fibonacci, right? I had a lot of you've heard about Fibonacci numbers. If you didn't, this is essentially the math for it, right? So for n equals 0 and 1, the output is essentially, for n equals 1 is essentially 1. And then every number, next number, is essentially the sum of two previous numbers, right? So essentially, like Fibonacci of 3 would be a Fibonacci of 2 plus Fibonacci of 1 and so on, right? So this is a very well-known function in math. I use in many different contexts. So how we would build an assembly for it. So similarly to how we approached problem before, remember, the first step is assign register names to variables and determine which is base case and which is recursive. That's critical for the recursion. Only one input n is passed in the register as a parameter. And in this case, we're going to use the register, say A0. And the base case is the then clause. The recursive case is the else clause in this case. And essentially, this is the code that's written here. This is the code for the base case, right? So you had a branch comparing to whether you're, more than one or not. If yes, you branch to some label called recursion that we show in the next slide. and otherwise we set up everything for the return value. Okay. Okay, so what we do next? So we need to save call and caller registers, right? So this is the start of the code. This is what we need to prepare the call. So we essentially need to store 3 registers to the stack. Array is the first register, A0 is the second register. We cannot assume so for example, A register will not be overwritten by callee. Array T0 is just a typo. I just forgot the space there, so there should be a space here. Sorry about that. Okay. Okay, and then essentially, then we need to do Fibonacci recursively, right? The way we do it is we compute n-1, right, by doing this instruction. And then we had, jump to the Fibonacci again, right? That's how we do recursion. And then we store V0, the third register, to be stored on the stack so it doesn't get overwritten by the callee. Okay. And then we need, remember Fibonacci has 2 recursive calls, right? So we need to set the second recursive call. And again, we retrieve the original value of n. We gonna reduce A0 by -2, and then we jump again to Fibonacci, to the base case check, okay? So this is how we do 2 recursive calls, right? But you see, we still didn't do the rest, like we still didn't do addition of them. So what we need to do then, we need to retrieve first function result and then add it to V0, and then we retrieve the return address, right? And fix everything on the stack and return the results. So that's essentially it, right? So we get everything added, fix everything on their in terms of return addresses, and yeah, so that's essentially how it would work. So it's relatively straightforward. I leave all this code for you on the slide so you can study it on your own. Obviously, I didn't ask you to write it right now because it would take some time. But this is, you see the strategy you do with assembly. You do everything step by step. So once again, right, you decide on which registers you want to preserve and what's important, what's not. Then you set up the base case, and you convert the code for the base case. That's usually very straightforward for all these recursive functions we may ask you to write. And then you write the recursive part that has 2 calls, but before that, you need to set up everything for the stack. And then you essentially call recursion twice, right? And as you get back, you essentially have your registers as an output. After the recursion, you add them up, right? And then you're done. Okay, any questions? Okay. Okay, if there are no questions, that's pretty much what I have for today. Next week, the whole Wednesday class will be dedicated to preparing for the exam. So I'm gonna bring up a few problems for you, show you some examples on how they can be solved, maybe ask some questions to you on solving certain things. And that's pretty much it. I still didn't decide what we're gonna do for tutorial next week, if it's needed or not, but the whole Wednesday gonna be definitely dedicated to preparing for the exam. Okay, any questions? Yeah, so if you guys have any questions for the quiz, as usual, please post them on Piazza so we can go with TAs and check whether everything is correct or not, other than posting it here. If you had any generic questions, Ivan, I'll check with the TAs. I'm not sure we're gonna have a next, I'll need to check whether we had next week's lab or not, or you will just keep working on the project, that's it. I don't think there is anything else other than the project is needed. I'll check with them. Cache masking problems on next, like, yeah, cache, there will be definitely cache questions for sure next week. We'll definitely go over it. So cache masking, I think what he's referring to is how to manipulate the bits when we look at the cache misses gets hits. So like, how do you decide which bits go where, how many bits for offset, and all those things. Yes. Okay. There is no quiz next week. So essentially that was the last quiz, right? So there's no more quizzes. So you'll be now just preparing for the exam. So probably if we have a class on Friday next week, I'll decide that, then it will be all dedicated to your questions. Okay. Any other questions, guys? Okay. So there are no questions, and thanks everyone. I will be here for a few more minutes, so please send a message if you want to meet with me one-on-one. Otherwise, have a great weekend. Thank you, guys. Yeah, thank you guys as well.